In the name of God. Hello, my dear friends. I am Gorbangol Ashabi, and we are continuing circulatory system. Blood circulation. In this part, we want to talk about formula of spring constant, Laplace law and Ohm's law, Poisson's rule and its experiment, and also we will talk about resistance and its relation with conductivity. After that, we will discuss measurement of flow and the way that flow is measured nowadays, and introduce electromagnetic flow meter to you. Here we want to focus on vessels' function and their behavior under different situations. If we imagine vessel as solid, solids are divided into two categories, elastic and plastic. Plastic solids are shapeable like iron, like wood, and it's not the changing of their shape is not reversible, so it's shapeable and irreversible shape. But the other solid as elastic is reversible and resilient like vessels, and we can change its shape, and the shape can back to the main shape. So for elastics, imagine an spring that is floated by an weight as m, and spring, you can see spring floats the weight. So based on a formula, delta L is equal to L by F by K. So what is these abbreviations, divisions? L is initial length of spring, delta L is changes of the springs during increasing the weight. F weight of hanger, and K is related to composition of spring, and it's a constant number for each spring. So if we enhance the weight, the F and L and also delta L is changed. So imagine we enhance the weight. When weight is enhanced, the delta L is changed because the second L is enlarged, and we can see different F or force for this spring. This is the main idea of Laplace law. So let's see this idea and this rule in our vessels. When we want to relate the last previous formula to the tubes, we can change some parameters. For example, imagine L as radius or R and F as pressure or P. So if we remove K or constant digit for each spring, we have delta L. Delta L is named as tension of the wall of vessel and abbreviated as T. So the formula is changed to T equal P by R in the tube. So in the elastic tubule, changes in legs alter to changes in radius. So they are directly related with each other. The pressure which pushes the wall of the tube depends to blood pressure multiple to radius. You can see each definition and abbreviation for each T as tension, radius as R, and blood pressure as P. And for spherical environment or spherical vessels, we have T equal PR divided to 2. So, what's the importance of Laplace law in circulatory system? Let me show this importance by an example. Imagine the radius of a vessel or a capillary is 1, and the pressure of that capillary is 30 millimeter of mercury. So the tension to the wall of the capillary is 30. So what happens if pressure increase from 30 to 50 millimeter of mercury? When pressure increase, the radius and the diameter of the capillary increase too. Imagine pressure increased to 50 and the radius increased to 1.5. So what happened? The tension of the wall increased to 75, from 30 increased to 75. So this formula show us tension is directly related to blood pressure and radius. If blood pressure increase, radius is increased too. And why our capillary is very narrow? Because of its reduction of the effect of tension on its wall. Because if tension is going to be high, maybe tearing or breaking of the wall of the capillary is happen, such as during some disease like aneurysm. The radius and the pressure of the wall of the vessel increase, so tension increase too, so the chance or rate of tearing of the wall of the vessel increase. So it's a it's not a good situation. So because of that, we can see very narrow diameter in the capillary because tension reduced in the wall of the capillary, and we can see very high radius or high diameter in the aorta, because the wall of the aorta can tolerate the high tension, but wall of the capillaries cannot tolerate against the high level of tension. Let's see Ohm's law in the physics and relate it to the circulatory system. You know, and you can remember from physics, V as voltage is equal to I as current multiple to R as resistance in Ohm's law, and we know this equation as Ohm's law. So we can relate this to the circulatory system. Imagine V as delta P, or changes in pressure inside the vessels, and I or current as flow or F, and resistance is the same. So we can change Ohm's law in the physics to delta P equal F multiple to R. Changes in pressure is equal to flow by resistance. So let's see, we can find F and R by this equation. Here you can see F or flow can be calculated as delta P to R, or R can be calculated as delta P to F. So here you can see which factors has impact on blood flow. A scientist named Poissier did some experiments and found which factors has a role on blood flow. Finally, he found this equation. And in this equation, you can see flow has influenced by delta P or changes of pressure, R as radius, eta as viscosity, and L as length of vessel. He did some experiments. In first experiments, he set up two vessels and pressure of one vessel is double to the next vessel. So he found the blood flow is increased doubled in the double pressure vessel. So he found pressure has direct connection and relation with flow. In the next experiments, he increased the viscosity of the fluid, and he found the changes of the viscosity of the fluid increasing the viscosity of the fluid reduce the blood flow in the same percentage. For example, if the viscosity increased in double, the flow reduced in double too. And also the length. The length has reverse connection with flow. If the length of vessel is increased as forcefold, the flow reduced as forcefold too. And finally, he found the impact of radius of vessel on flow. And as you can see in this equation, radius to the power of 4 has effect on flow. For example, if the radius increased fourfold, the flow increased to 256 fold. So this shows a little increase or decrease of the radius has a great impact or effect on the blood flow. So changes of the radius a little can increase or decrease largely the blood flow. Finally, he found this equation and create this equation based on their experiments and add 8 to the bottom of fraction and p to the upper part of the fraction. And we can say increase in radius could increase flow. Increased vessel length and viscosity reduce blood flow. So we can change radius, viscosity and length of vessels to change the flow. We need flow, so we should increase the flow, but we may not work on pressure. Why? Because pressure has a great impact on heart, and if we want to increase the pressure, heart should work a lot, and working and activity of heart should be increased, and this is not good idea because we want to change some other factors instead of pressure to increase the blood flow. For example, we can change the viscosity. How we can change viscosity? We can donate blood to increase the viscosity and decrease the viscosity and increase the flow. Also, we can change vessel length. How we can change vessel length? The amount of vessels will decrease by reduction of weight. If our body weight decrease for 1 kilogram, the length of vessels decrease about 3 kilometers. So this is another important factor. And the other important factor is changing the radius. The radius changing is very simple and we can achieve to it. How? By activating sympathetic nervous system, we can change, reduce and increase flow. So let's talk about resistance and found resistance relation with the Poisson's law. If you remember, we said F as flow is equal to delta P to R. So, and we know F is based on Poisson's law is equal to delta P PR4 to 8 eta L. So if we want to equilibrate these fractions, we can put them in continuous with each other and solve this equation. By solving this equation, we can find R or resistance. So R is equal to 8 eta L to PR4. So we know what factors has direct effect on R and what factors has reverse effect on R. As you can see, we can find resistance by measurement of pressure and flow, and also we can find resistance by measuring viscosity, length and radius of the vessel in that point. As you know, resistance or R can find by measurement of delta P or changes of pressure to F. So if the pressure difference between 2 points is 1 millimeter of mercury and flow is 1 milliliter per second, the resistance is said to be 1 peripheral resistance unit or PRU. The unit of PRU or resistance is din to second by second to centimeter to the power of 5. So in the blood vessels we have a unit for resistance named PRU. And let me say another example. The pressure difference from the systemic arteries and systemic veins, if was 100 millimeter of mercury and the average of blood flow is 100 milliliter per second, the peripheral resistance named as total peripheral resistance is the same 1 PRU. Okay, so you can find partial peripheral resistance unit for each part. For example, if the pulmonary arterial pressure and vein was about 14 millimeter of mercury and the cardiac output or flow was 100 milliliter per second, the total pulmonary vascular resistance or partial vascular resistance for pulmonary part can be 0.14 PRU. So we can find R as resistance for each part in our body. So what is conductivity or conductance? Conductance is a measure of blood flow through a vessel for a given pressure difference. The unit of conductance may be milliliter to second per millimeter of mercury of pressure, and conductance has is opposite of resistance. So we can say conductivity, or abbreviated as C, is opposite of resistance. And which factors, any factors that has a rule on resistance can change conductivity in a reverse form. For example, you know, reduction of diameter into the power of 4 can increase resistance. But how about its rule on conductivity? Yes, that's right. Increasing diameter to force-fold has a direct connection and relation with conductance or conductivity. So we can find C as conductivity to PR4 to 8 eta L. It's reverse of resistance. So let's find velocity by these formulas. If we remember from the physics, flow as I is equal to velocity or speed to PR2. So if we want to solve these two equations, Poisson's law and velocity's formula from physics, we can find velocity as V, abbreviated as V, as this formula. And finally, in this formula, velocity has a relation with cubage of radius and pressure, and also has a reverse relation with eta, viscosity, and L as length. One important thing in this formula is that flow is influenced by force-fold of radius, but velocity is influenced by second force of radius, second power of radius. Why this is important? In the vessels, when some vessels want to divide to the other smaller vessels, if the velocity or speed or the speed of blood flow was higher, they cannot turn into the smaller vessels. Like imagine like you are driving by high speed in a road, and if you want to turn to another road, you have to reduce your speed, unless you cannot turn to another road properly. This is why the radius has lower effect on velocity rather than flow. You can see if radius increased or decreased has a greater impact on flow rather than velocity. So this rule of radius on velocity helps blood flow to turn to another vessels during the blood circulation. How flow is measured in laboratory or in clinic? Before finding the apparatus for measurement of flow, let's talk about Fleming's right-hand rule. Fleming's right-hand rule said that under a magnetic field, if we have a motion, we can produce a electrical current as I. So this is the basic of all generators. For example, bicycle. The simple bicycle has a simple light which work with motion of bicycle. How this light of bicycle is turned on? When we ride the bicycle and in the magnetic field, we can produce the current, and this current and voltage can turn on the light of bicycle. So this is the basic of measurement of flow in the laboratory and clinics. Also, we have Fleming's left-hand rule. Fleming's left-hand rule said under magnetic field, if we give current to some engines, we can produce movement. For example, for fans under a magnetic field, take current and take voltage and produce movement by moving the blades of fan. So it's for motors. So we have two rules, and each rule is doing for generators or for motors. So how we found flow? Flow can be found by two ways. One of them is electromagnetic flow, which based on Fleming's right-hand rule. In the electromagnetic flow, the vessel is going to be under magnetic field, and the movement of blood flow can produce the voltage, and by finding the voltage we can find the blood flow in the vessel. So movement in magnetic field can induce electrical current and record this current by a receiver, and finally we can find the flow. This is another figure for electromagnetic flow meter. You can see electromagnetic flow meter is U-shaped, and it's going to be around the vessel and produce magnetic field, and by producing magnetic field we can find the voltage, and by assessing the voltage we can reach to blood flow in that vessel. Electromagnetic flow meter was introduced early, and it's not suitable for now. Why? Because if we measure the flow in one part of our body, we don't know which vessel is going to be measured. And the other thing is that we cannot measure the blood flow in our trunk or in our abdomen. So this is a good method for measuring blood flow, but because of its limitation, the scientists find another way to finding blood flow. Did you hear the voice of car? It's Doppler effect. We want to discuss Doppler effect. What is Doppler effect? Doppler effect is that if a phonic object or a sound object is going toward to you, you can hear the voice with high frequency and low amplitude. So high frequency and low amplitude can be achieved by our body when a phonic object is going toward to us. But what happens if the object is going away from us? If the object is going away from us, we can find the voice by low frequency and high amplitude. So based on this figure, you can see when object is going toward us, we can find by high frequency, and if the object is going away from us, we can find this sound by low frequency. As you can hear the voice of car in the beginning of this slide. This is the basic of Doppler effect, and the scientists use this effect to finding the flow in the vessels. So based on Doppler effect, we have Doppler ultrasound flow meter, and this Doppler ultrasound flow meter finds the object inside the vessel, for example red blood cells, and measure by sending the ultrasound to that vessel and finding the same sound by receiver and calculating the distance of the red blood cells from the giving the ultrasound to receiving the ultrasound, and finally find the blood flow inside the vessels. After that, we found Doppler laser flow meter, because laser is very suitable rather than ultrasound. Scientists used laser for this Doppler effect and produced laser Doppler flow meter, and the same thing is happened for this measurement of blood flow. So nowadays in the clinic or in the experimental situation, we use laser Doppler flowmetry to find the blood flow in our vessels. Dear friends, thank you for your attention to me. If you have any question, please ask me.